Hi, this is Nathan Tintle. In this Learning Goal video, we will talk about doing one overall test versus many tests which compare different proportions when you have two categorical variables. We will use the coming to a stop example to talk about this learning goal. In the coming to a stop data set, there's two categorical variables. There's the type of car. It arrives as a single vehicle, it's the lead vehicle in a group, or it's one of the following vehicles in a group. And another categorical variable, the response variable, whether or not the car comes to a complete stop. The difference here in what we've seen from earlier in the course is that there are multiple categories for one of these categorical variables. Up until now, we've just seen cases where both variables have two categories. They're both binary variables. So the question is, how do we evaluate whether the type of car is associated with whether or not the car comes to a complete stop? Well, one thing that we could do, knowing techniques we know already, is we could compare the proportion of cars that come to a complete stop when they arrive as a single car versus the proportion that come to a complete stop as the lead car, single versus following, and lead versus following. We could do three different tests comparing those two proportions. But there's a problem, and the problem is type 1 errors. Imagine that the null hypothesis is true. That is, all of the stopping proportions are actually the same. If we do these three different tests, each at the 5% significance level, then each test has a 5% chance of being wrong. That is, if the null hypothesis is true. This is what it means to make a type 1 error and the relationship between the type 1 error rate and the significance level. So the question is, if we do three tests, each of which has a 5% chance of being wrong, what's the overall chance that at least one of these tests has made a mistake? Well, the actual math's a little complicated, but it's quite a bit more than 5%. So what's the solution? Because we'd like to minimize the chances that we make these kinds of mistakes, these type 1 errors, these false positives. Well, the solution is to do only one overall test at the beginning and control the type 1 error rate at that point with the significance level. Let's talk about how to do that. The null hypothesis is that there's no association between the order the car arrives and whether or not it stops. What this means then is that the proportion of cars which come to a complete stop when they arrive as single cars is the same as the proportion if they're lead cars and the proportion if they're the following car. The alternative hypothesis is that there is an association. In other words, that at least one of these proportions is different than the others. Notice this isn't that all of the proportions are different from each other, it's just that at least one is different. So the goal is to do a single test of these hypotheses. Notice that the structure of these hypotheses, no association for the null hypothesis, there is an association for the alternative hypothesis, is very similar to structure we've seen before. So we'd like to apply the 3S process. Compute a single statistic, do a simulation of the null hypothesis, that is no association, and then evaluate the strength of evidence. In other Learning Goal videos, we'll talk specifically how to implement this test and what statistic to use. One word of caution, we're going to do this overall test. Is there an association between these two variables? We will do multiple tests to follow up a significant result. We'll talk more about that idea in other Learning Goal videos.